I'm going to give a brief overview of what we've been looking at in the field of primarily differential calculus. So, in other words, what do you need to know about calculus? And rather more importantly, why do you need to know it? So, here's just some background. What I'm going to do in this lecture is primarily give a review of the main topics that were covered in some of the earlier lectures. However, I'm also going to give a couple of worked examples of the typical questions you may see. So the main topics we looked at, this notion of what a function is, in particular line functions, and their properties. I introduced this idea of the first derivative as a method of describing changing gradients of a function. We looked, and this is a really significant part of calculus, at the notion of optimization and this technique called the second derivative test, which is applied in optimization studies. And to finish off, we looked at the development of standard single variable functions to multivariable functions and this concept of partial differentiation. So, functions and lines. A function is just a way of stating, of describing how some input value should affect what the output is. So it's a way of describing what happens when an input number has a function applied to it. And we focused on linear functions, on line functions. So these take the form, the function is described as some value m, which we call the gradient of the function. This multiplies the input, and to the outcome we add this quantity called the offset, denoted by c. Sometimes I'll write a line function in that style. More often I will write it in this form here. So one of the main attributes of line functions is that if we take any distinct pair of coordinates, there is a unique line function which contains that pair of coordinates. If we take any value for the gradient, this parameter here, and a single point on that line, then there is a unique line function with that gradient and containing that point. So what do you need to know? First of all, the formula which given any 2 points describes a line function connecting those 2 points. You don't need to memorize that formula, you can look it up. This is the formula here. The value of the y coordinate, the vertical coordinate, is given by that computation there. There is also a formula for finding a particular coordinate which is on a line with a specified gradient and contains a specified point. Why do you need to know these? Functions describing the gradient of lines touching a point on a curve, like this here, these are the basis of differential calculus. And they give rise to this notion of what I called the first derivative of a function, which we use this notation to describe. Those cases where that function, the first derivative, takes a value 0, these are important to what I call optimization problems. And these points, these are called critical points of the function, and they indicate where it achieves a local maximum or a local minimum value. So here's an example. Typical sort of question you might see is you have some object, such as a cyclist, who has a particular starting point and they travel from that starting point to the top of a hill at another position. That's what cyclists do. And you're asked what's the gradient of the hill. The sort of question you might see is at what height have they reached after they've traveled a particular horizontal distance. So the gradient is a measure of how the height changes relative to how the distance has changed. So in this particular case, we take the height reached, 495, we subtract the height started from 45, 495 minus 45, that's 450. We divide that quantity by the difference between the x coordinate, the final horizontal distance reached 65, from the starting horizontal distance 15. 65 minus 15 is 50. So we get the gradient is 450 divided by 50, which is 9. For the positional question, we find that the height reached when the distance traveled is 40 units. This is a value when the gradient has to be equal to q, the actual value we're looking for, minus the starting height, and all of that is divided by the height that the horizontal distance that we're interested in, 40, minus the horizontal distance we started from. In other words, that turns out, if you do the calculations, to be 270. What about first derivatives? What do you need to know about those? The first derivative is a function. It's a function which describes the gradient of the line touching a particular point on when we plot the curve of a function. The values we're of interest with the first derivative are those values for which the first derivative has the outcome 0. And these are called critical points of the function. And a function may have no critical points at all. It may only have a finite number. It may have infinitely many different critical points. Why do you need to know this? Critical points correspond to the gradient of the line touching a curve being 0. So these points correspond to places where the gradient is a line horizontal to the x-axis. That's what having gradient 0 means. And these describe potentially local minimum or maximal value cases. So as a result, this notion of first derivative, this notion of critical point, this is central to a subject called optimization theory. And this is the field of computer science which is concerned with finding the best settings for different parameters. It can happen that sometimes critical points don't yield useful information. So here's an example question you might see. Is you're given some function and you're asked to find its first derivative and to state whether this has at least one critical point. So we might have a function such as this example, or this example, or this example. How do we go about solving those? Well, first of all, let me stress again. I gave tables of rules for calculating, for computing first derivatives. Look them up if you need it. Don't try and memorize tables. So we take this first example. First derivative of 5 minus x squared all squared. Well, we have 2. We multiply this by the term in bracket, so we get 2 times 5 minus x squared times, then we have to differentiate this term. That gives minus 2 times x. And we look at this function, it is 3 critical points. 3 values of x, which make the first derivative take the value 0. One of those is when x equals 0, because this quantity will be 0. The other 2 are plus or minus the square root of 5, because then this term will become 0. We take the second example there, e to the x multiplied by the log of x. If we differentiate that function, we find its first derivative is this expression here. And this function has no critical points. There is no way of choosing a value of x which makes the first derivative take the value 0. Our third function, x squared times the cosine of x. This is infinitely many critical points. There are infinitely many choices of x which will make this take the value 0. I mentioned optimization. The key to optimization is this notion of the second derivative of a function. So what you need to know is how to apply the second derivative test to a given function. How do we do that? The first stage, you find the first derivative of the function. You then identify all those cases where the first derivative takes the value 0. In other words, you identify all of the critical points of the function. You then find the second derivative of our function. In order to do that, all you do is to differentiate the first derivative. And then for each critical point that you've discovered, you find the value of the second derivative at that point. If that value is positive, then the critical point you're dealing with is a minimum. If it's less, if it's negative, it's a maximum. And if it's 0, well, you can't make any conclusions directly at all. So, why do you need to know about the second derivative test? It's because of its application in optimization theory. Optimization theory is a discipline of major importance in modern computer science. There's a specialist final year module dedicated to optimization theory. The second derivative test, this is just one very basic mechanism that's used to apply to optimization problems. So let's look at an example. If we take the 3 critical points we discovered earlier of this function, look at the first derivative, we saw that that is 2 multiplied by 5 minus x squared multiplied by minus 2 times x, this term here. If we simplify that, we see that the first derivative is minus 20x squared plus 4x cubed. We saw that the critical points, there were 3 of them, are 0 and plus or minus the square root of 5. How do we analyze those? We find the second derivative, so we differentiate this function, and we get minus 40x plus 3 times 4, which is 12x squared. We evaluate the second derivative at each of the critical points, and we find when we evaluate it at 0, we get the outcome 0. So we can't deduce anything about the behavior of this function at that particular critical point. When we evaluate this function at the minus the square root of 5, we get a positive value. When we evaluate it at the positive square root of 5, we get a negative value. And so that tells us that the negative square root of 5 is a minimum critical point because this is greater than 0, this is positive. On the other hand, the square root of 5, positive square root of 5, describes a maximum because the second derivative is negative for that particular value. I'm going to move on to partial derivatives. So this is multivariable functions. What do you need to know in that case? You need to know how to form the first partial derivative with respect to a specified variable. You need to know how we define critical points in the case of multivariable functions, how to analyze those just in the two-variable case. The multivariable case, more than two variables, that starts getting quite complicated. Why do you need to know this? If you look at real-world applications of optimization, then very rarely you find that you're dealing with setting a single parameter. The use of partial differentiation and partial derivatives, this provides one way, admittedly quite a computationally costly way, of dealing with what we might call realistic optimization problems. So here's just a quick recap of what goes on. We have an n-variable real-valued function, such as this. We denote that as a function over the reals, so it's n real inputs, a single real output. The first order partial derivative of that function with respect to one of its variables, we use this notation, and it's constructed by differentiating the function as if the variable of interest were the only variable present. So in other words, we treat all the other so-called variables as if they were constant values. And a point is a critical point only if for every single first order partial derivative, for every single variable, the value of the partial derivative at that point when we evaluate it is equal to 0. So we have a problem involving simultaneous equations here. The conditions needed to classify to classify critical points are much more involved in this case. So here's an example question you might see. You have some two-variable function such as this. You asked to find the first order partial derivatives with respect to each variable and to identify if there are any the critical points of that function. So we form the first order partial derivative with respect to the variable x. So in this case, what we're doing, we treat terms in y as if y was a constant. X is a variable, so we differentiate 3x squared. We get 6x. This y squared term disappears because it's a constant. We differentiate this term, we get y. We differentiate 6 times x, we get 6. We differentiate this term, y is treated as a constant, so that term disappears. We then form the partial derivative with respect to y. And this time we're treating x as if it was a constant. So this term disappears. We differentiate that term. We get 2 times y. We differentiate this term. We get x. This term disappears. And when we differentiate this term, we get the value 2. To find the critical point, we need to find values which make this function equal to 0 and at the same time make this function equal to 0. So therefore, let's satisfy these two conditions. If we look at the simultaneous equations that result, what we find is that one of those values is minus 10 divided by 11, and the other value, the value for the second parameter, is minus 6 over 11. If we do the analysis of the second derivative test, we find that this satisfies the conditions for the point, the critical point, to be a minimum value. So let me just summarize things. Differential calculus is an important supporting method in the study of optimization theory. So this is the subject that is looked at on this particular final year module. Optimization problems, they arise when we're dealing with analyzing large data sets in process control applications, for example in setting cost and production parameters, and a whole host of other arenas. In that sort of application, very often we find that the functions modeling the environment depend on several variables. Typically, we're looking at the order of several hundreds or even several thousands of variables. And the analysis of partial derivatives, that indicates that in principle, despite the computational expense, differential calculus may be applied to solve those problems.